Welcome to the presentation of the final project of the Artificial Intelligence course. My name is Sri Manikanta.
This is Ram Nikhilesh Mekala.
Our project is trying to predict the class of cancer based on the clinical literature reviewed by experts and researchers from the field. Machine learning has demonstrated truly life impacting potential in healthcare, particularly in the area of medical diagnosis. To demonstrate how machine learning and deep learning are able to provide a medical diagnosis, me and my teammate will walk you through a step by step example of how the technology can be used to classify cancer using a publicly available dataset.
This dataset we have obtained from the Kaggle from Personalized Medicine Redefining Cancer Treatment. Here we have two files. One is training variant and one is training data. In training variation we have gene and variation, and in training data we have the text. The text is basically provided, it is a clinically literature evidence provided. And our aim is to classify 9 different types of cancer using this gene variation and our text. And we have 3000 plus instances to perform this activity.
So basically this is our project overview and these are the steps that we have followed through to complete the project. So we are going to be dealing with a lot of text data. So the first step in preparing the data for the machine learning models is cleaning it. And by cleaning, what we mean is basically removing the stop words, replacing the special characters with spaces, and converting all the text into lowercase. And we have, and when analyzing the data, we have seen some text rows where there are some empty values, and we have filled those corresponding values with the corresponding gene and variation values by concatenating them. And now we are going to use a term called TF-IDF. TF-IDF, what it basically means is a statistical measure that evaluates how relevant a word is to a document in a collection of documents. So we are going to use this technique to construct a word embedding vector and to apply one-hot encoding to the gene and variation feature using the TF-IDF vectorizer attribute from the sklearn module. And now Ram will explain you on average word to vec model.
The main reason why we are using the average word to vec model instead of TF-IDF is here we are going to deal with the text data. When we are dealing with the text data, the semantics is a very important. Average word to vec model does a very good job in this. Let us see how the average word to vec model is constructed. Let us have a review R1 which consists of words W1, W2, W3, W4 and W5. Basically the average word to vec model does is it will build a dense vector for each and every word with a d-dimensional vector. More the dimensional, more the powerful model, and we can, if we are having the more text data, the word to vec model does a pretty really a good job. Now let us see how an average word to vec model works. Okay, when we consider a review R1, in review R1 we have words from W1 to W5. So the first thing is basically it will construct a d-dimensional vector for W1, W2, W3, W4 and W5. So then it will sum all of these vectors and then it's gonna divide it with 1 by n. N is the total number of words in the review. Now let us see the code, how average word to vec model is constructed. Here we have constructed a word to vec model with the help of a Genesim framework. So I have passed parameters of list of sentences. The list of sentences I have given all my training text data, and min count equal to 5, this is a parameter. So the model will take only the words which has occurred more than 5 times, and we have given the size equal to 200. 200 means here we are going to construct a dense vector of 200 dimension. Now I'm going to walk you through the code. I have defined a sent vectors list, and then I have defined one more sent vectors of np.0 of 200. This 200 is we are going to construct it to the 200 dimension vectors, and then I have passed the each and every word to it. You can see that vec equal to word to vec model dot word to vec word. So basically it, what it does is it will calculate the each and every dimension and store it in the sent vectors, and we have initialized the counter. See, we see this count words is used to finally divided with it the whole vector. Sent vectors equal to the sent vector equal to sent vector divided by total number of words. Now let us see the code. Now I'm not going to run this code because it's taking huge time. So you can see just for 997 reviews it take nearly 24 minutes from this. And After performing this, we have normalized our data in order to avoid the overfitting of our models. So, and then we have stacked our models merged into a single dimension with the help of a head stack function. Previously Mani told we use TF-IDF vectorizer to perform the one hot encoding on gene and variation. So you can see the train gene feature one hot encoding code on the top, and here we, with the help of a hstack function, we have merged two arrays into a single array. So you can see the gene feature one hot encoding and variation feature one hot encoding. With the help of hstack, we have merged into train gene variation one hot encoding. And then with the help of same thing, we have performed one hot encoding on the text data also. So we are merging both train gene variation and text data into a train X one hot encoding. And now Mani is going to explain about the machine learning models.
So before building the machine learning models, what we have to do is the hyperparameter tuning, and we are going to be using a class called grid search CV. Grid search is the process of performing hyperparameter tuning in order to determine the optimal values for a given model. This is significant as the performance of the entire model is based on the hyperparameter value specified. After performing the grid search, we are going to be looking at two basic sets of models from machine learning, which are support vector machines and Namebase classifier. In support vector machines, we have taken the linear kernel and the RBF kernel, which is the radial basis function kernel. And in the Namebase classifier, we have decided to go with the multinomial Namebase, as this is a multi-class classification problem.
Okay, the main reason here we are choosing the evaluation matrix as multi-class log loss and confusion matrix for plotting how our model is performing. The main reason for choosing the log loss is, here we are, log loss is important for classification because it will give the estimates based on probabilistic features. And let's see what is an SVM. SVM is a support vector machines. It will just give as SVM is mainly focused on a planes. The linear SVM, it will try to give a plane to separate the data. The main linear SVM is used when our data is linearly separable. You can see from these two diagrams, SVM with a linear kernel and SVM with a RBF kernel. The main reason why we are using RBF kernel is we have plotted our data using the TSNE. TSNE is a T-distributed stochastic neighborhood embedding. It is used to visualize the high dimensional data. So I have passed our data into the TSNE component into a two-dimensional space. So you can see the TSNE data equal to model.fit transform. I have used the scent vectors. It's the scent vectors which are, we got it from the word to vec model. So when we try to print it, you can see our data is not linearly separable. You can see that from this we have the labels for each and every class. It has a different color. So you can see our data is not linearly separable. So when our data is not linearly separable, we are going to use the RBF kernel. Now I'm going to walk you through the code for this. This is the code for SVM with a linear kernel. Due to computationally expensive for the linear SVM, stochastic gradient descent with hinge loss does the same work. So we use the stochastic gradient descent to perform the SVM with linear kernel. So we have used the grid search CV, what Mani said. So we have given all our hyperparameters. So I'm going to run this code. So it will give the best parameters for our model. It's gonna take time because it needs to build the model with each and every hyperparameter. So we got our best alpha as 0.1. So again, when we give our alpha as 0.1 and then we have run our code, so you can see that we got the training loss and test loss as this, and this is a function to plot the confusion matrix, how our models are performing. So I'm going, so with the help of this code, predict y equal to clf.predict send vectors test. So we are going to predict our test data, and now I'm going to plot the confusion matrix for our data. So see, you can see this is the confusion matrix, how our models are performing with the linear data. Now I'm going to run the code for support vector machine with RBF kernel. Here also I am performing the same thing with the help of a grid search CV. Here these are all hyperparameters. C gamma is the basically hyperparameter if we are using the kernel RBF. So we are going to run this code because it's going to take time You can see we have using the 5 call, so it's gonna take 25 times, so it's gonna take more time. So let's pair this. Yeah, you can see it's using 0.1 as its C and kernel equal to 0.1, and you can see the scores, the time elapsed and everything. It's gonna take time, more time. Okay, it's gonna take time. Now it came to C1, so we'll come back to this later. And we have already run the model, so I'm gonna just give you the losses. These are for the SVM with a linear kernel. Due to our limitations, we use SGD. So we got the training loss as 1.129 and test loss as 1.725. And SVM with the RBF kernel, we got the losses. SVM with RBF kernel does a really good job because our data is not linearly separable. So you can see our training loss is 0.69 and test loss is 1.62. Compared to the linear, it's doing a pretty decent job. And these are the codes for linear, SVM with the linear and SVM with the RBF kernel. Let's check how our code is going. Yeah, it's still in 10 and it's gonna take so much time. Meanwhile, I think from my teammate, he's gonna explain about the Namebase algorithm.
Naive-based methods are a set of supervised machine learning algorithms based on applying Bayes' theorem with the assumption of conditional independence between every pair of features. Multinomial naive-Bayes implements the naive-Bayes algorithm for multinomially distributed data and is one of the two classic naive-Bayes variants used in text classification where the data is typically represented as word vector counts. So
And now he's gonna show about the code for the Namebase. Okay. And one more thing, this code is running, so we cannot run this. Just bear us within a minute. It's in 100. The code is running. Now we have entered into the final C equal to 1000. Okay, now Mani will explain how our confusion matrix is. What is a confusion matrix?
So this is the confusion matrix that we get after we plot the SVM model with the RBF kernel. So the x-axis represents the predictor classes by our model, and the y-axis represents our original classes. From the graph, we can see that the model has performed poorly when trying to predict the class 3, 8, and 9. And now Ram will give us a brief introduction about the deep learning models that we will be seeing.
Okay, before going to that, let us see how our code is running. Yeah, you can see that the model has done, and then we are going to print the best parameters. So you can see the C equal to 10 and gamma equal to 0.1 for the RBF kernel. So when we run this code, you can see that it's calculating the train and test losses for this. It's gonna take time. Yeah, you can see, and now we are going to predict our Y models. And for the confusion matrix, yeah, we got the confusion matrix. And then we are going to run the Namebase model here. For the Namebase, you guys can see we also did the hyperparameter tuning for the Namebase model, and we have tried to print what is the best value for the training and test. So it gives the best parameters at 1000 with the training loss of 1.1413, and these are the classes for this is a confusion matrix for this. And let us go into the deep learning models. In the deep learning models, we have choose the two latest models, long short-term memory LSTMs and bidirectional RNN for our task. Now Mani is going to explain about the data pre-processing. Okay, sorry, I'm going to explain about the data pre-processing. Here we are going to apply the one hot encoding to the gene and variation, and we are going to add it to the text column. So I'm going to walk you through the notebook which I have used this. So I have basically converted all our gene and variation into the one hot encoding, so it will assign a unique number to each and everything, and then I have appended it to our text data as a text final. And you can see in deep learning we need to use a different approach. So I have given ranks for each and every word based on their frequencies, how many times the words has occurred in our text. So you can see I'm going to walk you through that code. So I have assigned that result text to final into the clean text, and then you can see that we are, with the help of a counter, we are going to find how many times that each word has occurred, and then we are going to build our vocabulary. We are going to give the size of that vocabulary. So, and now you can see that we took just the top 20,000 most common words from our text. In this code, from here we are going to give the word and its frequency with the help of this code. So I'm gonna print this, so you can see the mutations and mutation word and its frequencies. Mutation and its word frequencies has 23,860 times it has occurred, and I have defined a function called ranking. What it does is, higher the frequency, the lesser the rank. So I'm gonna run this code. It's gonna take time because we have a huge corpus, and just bear with me a minute. Yeah, you can see that we have given a clean text index. So for dependent it has assigned a rank of 187, and regulate it has assigned a rank of 1292. So then we have splitted the data into test train, and then I have converted our classes into two categorical, and then we did the padding for each and every word, because in order to have the each and every review to be in the same length. So I run this code. You can see this is our embedding vector for our first review. These are all the ranks for each and every word. And now my teammate is going to explain about the long short-term memory.
So, since we are going to be dealing with text data, long-term dependencies are one of the most critical problems that we will be entering, and preserving the long-term contextual relationship is very important in our data. RNN is basically just a neural network which processes the information in a loop, but it has a very big problem, which is the vanishing gradient problem. LSTM overcomes this using the gates to retain memory, and we will be seeing the code for the LSTM.
So basically the LSTM, it's gonna take huge time to run, so I'm gonna walk you through the code. So we have defined an embedding vector length of 100, and as we are dealing with the text data, we need to give an embedding layer. So we have already see, you can see our vocabulary size is this much, and we have given our embedding vector length of 100, and input length equal to max review length. Max review length is the review length we have fixed before padding it. So we have given it as 375, so each and every review length will be 375. And we have added LSTM model with 100 units, and we have used a dropout layer here also. And finally we are predicting 10 classes. So we are giving the dense of 10 units with the activation of a sigmoid units. The main reason why we are choosing the sigmoid unit is sigmoid will give the probabilistic output for each and every class here. So let me walk you through this. Then we have fitted the model with X train and Y train. It's taking so much time, so I'm just walking you through this, and this is the final loss we got of 0.54 with accuracy of 0.38. And you can see this is the graph for how a model is performing for the training and testing data. And now she is going to walk you through with the bidirectional RNN.
Bidirectional RNN are really just putting two independent RNNs together. The input sequence is fed in normal time order for one network and in reverse time order for another. The outputs of two networks are usually concatenated at each time step. Here we have an update gate introduced in the GRUs to decide whether to pass the previous output to the next cell or not. So basically what it does is just to decide what information to throw away and what new information to add. And now Ram will be explaining the code related to the GRU unit.
Okay, the code is pretty easy because here we are using the Keras, so it is pretty similar to our LSTM. The only change here we are giving is just we are adding this layer, the bidirectional GRU. GRUs stand for gated recurrent units, so we are giving 100 units, and then we are adding one more layer of dense layer of 56 with activation ReLU, and finally we are giving the softmax as our activation function, because the softmax function outputs a vector that represents the probabilistic distribution of the list of all the potential outcomes we are having. And you can see this is how our model is model performance is, and we have the loss of 0.762 and accuracy of 83, and you can see the graph how our model is performing, and she is going to give you the conclusions about our project.
So here we have the log loss of all the 5 models that we have built, and you can clearly see that the bidirectional RNN with the GRU unit has outperformed every model by a very narrow margin. But still, as usual, like bidirectional RNNs take in the information of the context, so that's like more advanced and like very complicated compared to all the machine learning models that we have built. And this is our project. Thank you.
Thank you so much.